So now we'll consider two-dimensional flows with parameter. So, flows with parameter. So x dot is function of x, y, and parameter c, and y dot is function g of x, y, and parameter c. So when we have parameter, now when we look for equilibria, then equilibria are functions of parameter c. So this is function of c. This means that both location and stability of equilibria depend on parameter c. And this is, let's consider example. So this example also from your lecture notes, x dot equals to mu minus x squared and y dot equals to minus y. So here mu is parameter. So equilibrium, if we want to find equilibrium, we look for roots of algebraic system mu minus x squared equal to 0, minus y equals to 0. So from here we get y is 0, and from here we get x1, 2 equals to plus minus square root of mu. What we see, we have two equilibria, and they exist when mu is non-negative. So okay, we have two equilibrium. I will denote them as P1 with coordinates minus square root of mu 0 and P2 with coordinates square root of mu 0. So position depends, what we see, positions depend on mu. And next, what we want to do, to analyze stability. This equilibrium, to analyze stability, we need to find Jacobian. Jacobian of x, y is, we already were looking for this before. It is here derivative of f over x, here derivative of f over y, derivative of g over x, and derivative of g over y. So this is Jacobian at any point x with coordinates x and y. And now we need to find Jacobian at, say, P1. And Jacobian at P1 is 2 square root of mu 0, 0, minus 1. And eigenvalues are roots of this characteristic equation, 2 square root of mu minus lambda 0, 0, minus 1 minus lambda equal to 0. And from here we find that lambda 1 equals to 2 square root of mu and lambda 2 equals to minus 1. So this is P1 is saddle. And Jacobian at P2 is minus 2 square root of mu 0, 0, minus 1. And here here lambda 1 will be equal to minus the square root of mu, lambda 2 equals to minus 1, and this is stable node. In terms of bifurcations, what we can say, so we see that two equilibria appear when exist when mu positive and don't exist when mu is negative. So mu equal to 0 is, we called it before fault bifurcation, but for two-dimensional systems it's called saddle node bifurcation. So that when mu equals to 0, we get bifurcation, and there appear stable node and a saddle. So this is about bifurcation taking place in this particular example. So generally we can put it like this. For let's say we consider 2D flows. So this is complex plane. Here, let's say real part of lambda. Here, imaginary part of lambda. This is eigenvalues of Jacobian at equilibrium. If, let's say, this is lambda 1 and lambda 2. If both lambdas are real and negative, then we will have stable node. And since lambda 1 and lambda 2 are functions of parameter c, when we change c, lambdas can change. And for example, there can be a case when lambda 2, for example, becomes 0 and then changes its sign. And when this happens, this transition, lambda 2 crosses the origin, we will have, so here we have saddle node bifurcation. But basically, two other bifurcations also take place at the same, during the same process. When one of lambdas changes sign, gets 0, it changes sign. So this also pitchfork. And also transcritical. So this all three bifurcations which we observe in one-dimensional flows occur when one of lambdas, one of eigenvalues for becomes equal to 0. We can have lambdas imaginary. Lambda 1, 2, plus minus I beta. And here we know that if beta is non-zero, then we have focus, stable or unstable. And this now alpha is function of parameter c, beta is also function of parameter c. And so in this case, well, maybe I plot it again. Imaginary part of lambda. So we have two complex lambdas. This is, let's say, alpha plus I beta, and this is minus I beta. When alpha changes sign, we have this crossing alpha and changes sign. And when this happens, our stable focus becomes unstable, unstable becomes stable. And this kind of bifurcation is called bifurcation. And limit cycles appear in course of Hopf bifurcation. So non-degeneracy condition for Hopf bifurcation is quite complicated. I'm not going to show it here, but at least I will mention a little bit. I will note some critical points here. So when we have Hopf bifurcation, so we know that alpha is a function of C, but when, let's say, at C star, we have Hopf bifurcation, then alpha at C equal to C star should be 0, because, so here, on vertical axis here, imaginary part, real part is 0. And the first condition is derivative of alpha over C when C equals to C star is non-zero. It's first condition. And there is one more condition, and it is very long condition. It is certain combination, let's say, combination of second and third derivatives of f and g is also non-zero. This combination is non-zero. So it is long combination. I don't remember it myself, and I don't want to bother you with this. What is important? If non-degeneracy condition is satisfied, then our system at bifurcation point can be reduced to a certain normal form. So normal form if non-degeneracy condition satisfied, then we can reduce our system to normal form, which looks like this: x dot equals to, say, beta x minus y plus sigma times x squared plus y squared, and y dot equals to x plus beta y plus sigma times y, x squared plus y squared. And now we have two subcases. Sigma, so sigma is either plus or minus 1, sigma equals to 1 or sigma equals to minus 1. If sigma equals to minus 1, well, you don't need to remember this. What you need to remember is that we can have two cases for Hopf bifurcation. One case is, let's say, sigma equals to minus 1 is limit stable limit cycle exists when beta is positive. So this means that beta is our parameter now. So we change our parameter when beta is 0, we have Hopf bifurcation. If beta is positive and sigma equals to minus 1, we will have stable limit cycle. And if beta is negative, we don't have beta negative, no limit cycle. So in course of Hopf bifurcation, limit cycle appears or disappears. But when sigma is minus 1, it is stable. And when sigma is 1, it is unstable. Unstable limit cycle exists when when beta is negative. So we have two subcases, two kinds of Hopf bifurcation, and they like this for pitchfork. It's called subcritical and supercritical Hopf bifurcation. For supercritical Hopf bifurcation, we get stable limit cycle. So at the origin we have a spiral. Maybe I can illustrate it here. So there is a cycle, let's say stable, beta negative. Then when beta positive, it becomes unstable, but in addition we get limit cycle, let's say this, and our so there is convergence from outside and from inside and from outside also. So we have convergence of phase trajectories from inside, they get out and converge to right limit cycle, and from outside they also they get in but also converge to limit cycle. So right is limit cycle, stable limit cycle. And if we, so this is supercritical. Hopf bifurcation. It is one case, and subcritical. It is opposite. So we have unstable focus, stable focus, and this is unstable focus. And this unstable focus when beta is positive, and then it transfers to stable, and we have in addition unstable limit cycle here. So there is divergence inside and outside. So this is unstable limit cycle. Okay, this probably is pretty much all what you need to know about Hopf bifurcation.